Hello. Today we will talk about the forecasting Australian retired trade using time series analyzing. Our good name is HDS Group, and we're forecasting Australian retired trade from 2005 and 2025 using the time series analyzing forecasting focus on clothing and footwear sales.
Data visualization. This time series visualized monthly retail sales for clothing, footwear, and personal accessories in Australia from 2005 to 2025. We observed a strong upward trend with a sharp dip around 2020 due to the COVID-19, followed by a rapid rebound. This highlights both long-term growth and the impact of external shocks. The seasonal subseries plot reveals a clear seasonal pattern. December consistently shows the highest scales, like due to Christmas, while months like April and August are often lower. This confirms that seasonality is a key component in the data and should be included in our forecasting model. Looking at the ACF plot, we see slow decay and a significant correlation across many legs, which confirms that the original series is non-stationary. Meanwhile, the PASF plot shows a strong spike at leg 0.1 and then quickly drops, indicating that an autogressive term may be useful after differentiating. In summary, this pattern suggests that an SARMA model with both seasonal and non-seasonal components is approximate to capture the underlying structure in the data.
Bahrami for this seasonal data, I choose to apply this visual approach for finding model specification. After applying this model, there was a huge leg in the seasonal leg, spike in the seasonal leg. Then after applying these ordinary differences, the seasonal leg vanished, but there were ordinary legs. Now in this model, there are most of the ordinary legs vanish, but there are huge legs there. Then I use the residual of this model to find other model parameters. The first model can be 0, 1, 0, then the next one will be 1, 0, 1, and the next one will be 0, 1. After model fitting, we can check which model parameters are significant. In our first model, seasonal MA part is significant, which is below 0.05. In our next model, also both ordinary MA, seasonal MA is significant. In our third model, all the model parameters are significant, and all of them are below 0.05. In our third model, as usual, all the model parameters are significant, and in our last model, all the model parameters are significant except R2. Now we can perform residual analysis. In this section, we will check IC values, other error analysis, arch effect, normality, and autocorrection check. Based on this output, the third model has the lowest IC values, and the worst performing model is the first model, which has the highest of these values. Also, it has the highest residual mean square error value, and our third model has also a very low RMSE error. Moreover, all the residual of the models passes autocorrection check and arch effect check, which means that we don't need to perform Gauss modeling, but all of them fail in normality check. They are not normally distributed. The thing is, like, when we are performing seasonal forecasting for interval of points, we don't need normality check. Residual can be non-normal, and yeah, all of them are good. We can use one of them for forecasting. Now we can use the base model for forecasting. I have used this model to forecast the last 12 points of sales data. The red line indicates the actual sales data, and blue line indicates forecasted sales data. They are pretty much close, but here in this section, in the last section, there is gap between them. And this table indicates actual and forecast sales data. Also, it indicates error, absolute error, and percentage point error. The percentage point error shows that model has been able to forecast the sales data within 90% confidence interval, which is good, but the model also needs further improvement.